Hello everyone, welcome back to Electronics 1. This lecture is just following up on the last lecture where we looked at how to solve for the large signal and small signal operation of a diode. In this class I want to go through an example, and this example will have, again, a small signal component, a large signal or bias voltage, have a series resistance, and we have a diode, and we're interested in the voltage, the output across this diode. Okay, so we're going to call the small signal component Vs. We'll call the large signal component V bias, and we'll assume that the resistance is 10 kilo ohm resistance. Okay, the large signal component's a 10 volt source. My small signal component is 1 volt peak 60 hertz sinusoid. Okay, and you might think your first thought might be, well, one volt is much larger than what we defined as a small signal, but keep in mind that that entire voltage is not being applied across the diode, right? Some of that is going to get lost as a voltage drop across the resistor. Okay, so what else do we know about this diode? Well, the diode characteristic provided tells us that at a forward voltage drop of 0.7 volts, the diode has 1 milliamp of current flowing, and our ideal D factor is 2. Okay, so let's use the iterative approach, and let's do some bias calculations to start out here. And let's, for our first pass, let's solve for the voltage or the current through our diode. So we're going to assume that the diode voltage here, the diode voltage for our first pass is actually at 0.7 volts. Okay, and in which case we should expect 1 milliamp if that's true. So to solve for that current, again, looking at the circuit, the voltage across the diode, and again, this is just the bias case, so we're ignoring the small signal component for now. We're just focusing on the large signal voltage that's applied. Okay, so we can get the voltage across the resistor here as the bias voltage minus the forward voltage drop across the diode. Okay, so and I guess maybe I should show this as uppercase because I'm assuming this is just the bias at this point, and honestly I guess this is actually uppercase as well because this is just the current due to the bias. So the voltage across the resistor is the bias voltage minus our drop across our diode divided by the resistance, should give us the current through that resistor. Okay, plugging in our values here, 10 volts minus 0.7 volts divided by 10 kilo ohms gives us a diode current or bias current of 0.7 930 microamps or 0.93 milliamps. Okay, I'm no, I don't care to have any more precision than this in this for this particular example, so I'm going to say, since 0.93 is pretty close to 1 milliamp, that we're going to continue with this estimate and assume that this is close enough. Now you could iterate and get the current a little closer, but again, it depends on your application and whether that's necessary or not. Okay, so now I'm going to jump immediately to my small signal analysis, which is my second step. And yeah, bias calculation, my first step. This is my second step. So my second step, I'm going to ignore the bias component, and my circuit becomes very simple, right? My diode, which is forward biased, I can just represent with the small signal resistance. It's in series with my 10 kilo ohm current limiting resistor and my small signal AC waveform that has 1 volt peak. Okay, and I can solve for my output voltage across this. The diode is just across this small signal resistance. So knowing that my bias current was 0.93 milliamps, then I can solve for my small signal resistance because it's equal to NVT over my bias current. Right? So plugging in those values, be careful of your units here. I've got everything in milliamps, so the milli term is going to cancel here, and I'll end up with a small signal resistance of 53.8 ohms. Okay, so this in my small signal model is simply a 53.8 ohm resistance. So my output voltage here is calculated, just leave that off to the side here. My output voltage is simply calculated through a voltage divider, right? My small signal resistance divided by my current limiting resistance plus my small signal resistance times my applied signal. Okay, so my output voltage becomes 53.8 ohms divided by 10 kilo ohms plus 53.8 ohms times 1 volt peak. This is a peak level. So multiplying that out, and I get an output voltage that's 5.35 millivolts peak. Okay, and this is of a magnitude that is clearly falls into that small signal category. Okay, so what if we plot it, what this looked like, I'm going to plot my output voltage V. That's a uppercase O, although it's probably really difficult to tell here, where this is representing my mixed signal, which is my output voltage due to my DC bias plus my small signal component. Okay, and my bias is setting my output at 0.7 volts, so this is due to my bias. I guess I could be, I guess this is fine. Okay, and fluctuations around that bias are caused by my small signal component. And we just found that small signal is going to have well, we knew that its peak value was is 5.35 millivolts, so the peak to peak of this sinusoid that's riding on this 0.7 volt offset is 2 times 5.35 millivolts, or 10.7 millivolts. Okay, so this is my small signal component. The small signal output from this circuit. Okay, and the combination, the mixed signal, is that small signal that's offset now by 0.7 volts due to the bias. Okay, so that's how we would solve for the mixed signal operation of a diode, taking into account its bias and solving for the small signal aspects of the operation.